All right. So can you tell us more about who you are?
Yeah, my name is Venkat Narayanaswamy, and I am an associate professor at the Aerospace Engineering Department at North Carolina State University. I've been here for the past 9 years, and I'm originally from India. That's where I grew up. I was born there, and I spent the first 21 years of my life there, pretty much. So I went to undergraduate school there and got a degree in aerospace engineering. Came here, got another doctorate in aerospace engineering before I joined the academia. And I guess outside of academics, I'm interested in reading music, and I'm a movie buff. It's South Indian movie buff. Let me put it that way. So that's the brief history of myself.
Mhm. And why did you want to become an aerospace engineer?
To be honest, I never wanted to become an aerospace engineering until I enrolled into the aerospace engineering program. The way things work in India is we take an equivalent of this SAT exams that you guys take, and based on how you perform, you will be allocated essentially an engineering stream. Uh, I wanted to be an electrical engineer, and at that point, when I was in high school, it was very alluring, mainly because there are all these Googles and Apples and whatnot. That is, it has a it's a huge appeal in India, and so I was really hoping and planning that I would be in electrical engineering, but it turns out that the scores I got effectively got me into aerospace engineering, and that's pretty much how I did my undergraduate. But over the undergraduate degree, I started to develop a penchant. Um, Not so much that I was like super excited, but I started to getting an appreciation for what I'm learning and the technology that I'm getting into. Because what I figured out was that the aerospace engineering is effectively is the fountainhead of many other technologies. And most of the technologies that we see today are because there was a need in aerospace engineering. The satellite communication is a very simple example of where how the aerospace engineering effectively um, uh, germinated so many other technologies that we are using and we used as aerospace engineers. If you look at the history books, you will see that the satellite communications were used back in the 60s, so we will be the first user. We are effectively 30 to 40 years ahead of technology that is going to hit us 30 to 40 years later. So we are at the leading edge of the technology. We define pretty much the use of most of the engineering systems. So pretty much the kind of materials we use and the stipulations we put on the materials is going to be so high and so intense that the we define what is going to be the leading edge on many other technologies. So that excited me a lot.
Mhm.
And I also I liked math a lot and chemistry a lot, physics a lot. But what I found also was that the aerospace engineering is an amalgamation and a very organic and synergistic amalgamation of all these streams. As an aerospace engineer, I learn a lot of physics. Obviously, there is among the different engineering, I would argue aerospace engineering has the most intense and rigorous math, and we actually learn just as much chemistry as a chemical engineer would do. So it is a very rigorous program, and you will be very multidimensional, which gives you the flexibility to excel in many other fields than other than aerospace engineering. So once again, I never realized it when I was in high school. Thankfully, I got to the aerospace engineering program, and then I realized all these things, and I was so thankful I took this. I got into this program.
Mhm.
So yeah.
All right. So you mentioned the aerospace engineering. It is a collection of different and new technologies that are discovered. And why did you choose scramjet propulsion technology as your main area of research?
If you think about how trade and commerce has evolved and how the human civilization has evolved, you will see a distinct change in the way world has changed between 1903. I mean, before 1903, when the airplane was invented, and after 1903, the whole concept of global village happened because of aerospace, air transport. If there is no air transport, this global reach of citizens, like people from one place to the other, is essentially impossible. The next other option is ships. Okay, so you know how slow the ships are to go from one place to the other. So obviously aerospace technology is the way to go. And then when I said aerospace, now the what we are going after next is space, right? So commercial space access and shrinking the time between going from point A to point B anywhere in the world is going to be probably the biggest leap, I would argue, in the 21st century. So imagine you need to send an aid somewhere. Imagine there is a natural disaster somewhere. The faster you go or reach a particular place, the more lives you will be saving. So if you want to save more lives, you better reach the place fast. And not all places are going to have the best of amenities in their neighborhood. So you would need, if you shrink the time between going from one place to the other, it is a big humanitarian service. There is a huge humanitarian dividend that we will reap off of it. And these trade and commerce is going to immensely benefit. So there are a lot of local places which are not currently accessible by markets, just because they cannot travel to certain places, which will not be the case once you can shrink the time for travel. These examples include a lot of perishables that cannot stand more than 3 hours, you know. So so the question is, how would you, if you want certain perishables, how would you do it? And if you want to just take those perishables, can also include vaccines. We know that certain vaccines need to be stored at intensely low temperature, and they will lose their potency as you expose them to higher and warmer temperatures. So the question is, how do you keep their potency while reach a particular and deliver it to a particular place? All that means is you need to travel much faster than what we can do now. And that is why I'm so excited and interested in hypersonic and scramjet propulsion.
So how does scramjet propulsion work?
So at the heart of it, you can I share a picture? Is it
Uh,
possible at all?
yeah, go ahead.
Okay, so I'm disabled, but if you enable, I can share the picture. Um,
I think I have to make you a host for that.
you can do multiple people, participants can share,
Oh, right.
and
Okay.
that should.
That work?
disabled still. You can make me a host, that's fine.
Okay.
Yeah, got it. So, okay, so I believe you can see this picture.
Yep.
And I'm going to flip to another picture as well. So this is this is what is called an experimental airplane. It's X series, X51 is its name. So essentially the scramjet engine is right here. So this is the portion that we are going to talk about. So all your payload people, everything is up here. So we are going to talk about what's happening here. So let me just open another picture. Okay, and I'll share this. Okay, so this is what is underneath that big airplane. So at the heart of it is the fact that in a scramjet, you do not have any of compressors or turbines that is going to do work for you. And that in itself is an extremely elegant solution in that you are using the kinetic energy of the flow to extract the work without having any moving parts. We do it with what is called shock waves, and all these red lines are called, or what are called shock waves. They essentially, it's a naturally occurring process if you provide the conditions that makes it conducive for their occurrence. If you engineer, so this is where engineering comes at. So this is where how smart we can design things. So if we design the system smart enough, then we can reap a huge amount of benefit by letting the nature take care of the compression. So we are converting the kinetic energy to heat and pressure. And the reason you do that is you need certain amount of pressure to burn. Okay, so you pressurize the gas and you let it burn, and burning is essentially you're adding thermal energy on top of the kinetic energy that's coming in, and then you convert the stored thermal energy into kinetic energy by what is called a nozzle. So essentially, if you think about it, you have a compressor. In an engine, you will have a compressor, you will have a combustor too, and you will have a turbine and nozzle. Here, everything is done without any moving part. So it might, the elegance is the fact that, so I can 3D print an engine, and this is exactly what it looks like. And I can test it in my lab without, and this is what we do. And this is the elegance of the entire scramjet propulsion. And it also brings about a lot of challenges because it's very, very, very hard to make it as efficient as we want and to burn in these type of situations. So it comes with a lot of challenges.
So what are some of its positives and negatives compared to other propulsions such as turbofan and turbojet?
The biggest positive is that you don't need a moving part. You don't need a turbofan. Turbofan means there's the fan in the turbine. You need none of those. There is very little mass. It weighs very, very small compared to a turbofan, right? So that's very nice, right? Because you just weigh so much less, so you can just notionally you can add so much to the payload. But that's not the end of the story. That's where its limitations come from. The limitations come from the fact that it's not going to be very efficient unless you make it efficient. And a fundamental disadvantage is that a scramjet cannot operate at zero speed. You need to take a scramjet to a certain velocity before it can actually perform with any reasonable amount of efficiency you hope to get from out of it. So a scramjet always depends on a turbine cycle or a turbine for it to reach its starting speed. Once it reaches the speed at which the scramjet engine can operate, then you no longer need a turbine. But unfortunately, what we are looking at what is called a combined system, where if you want to take off from zero speed, like you're doing, then you need a turbine to take it off from zero to some speed where the scramjet can operate. And then you use the scramjet mode, shut off the turbine. The issue then becomes you are carrying two engines instead of one. That is the biggest disadvantage. So the biggest disadvantage is that a scramjet cannot start from zero speed. You always need two engines, a scramjet and a turbo, for you to if you want to imagine a like commercial transport, a commercial supersonic or hypersonic vehicle will look like two engines set in one platform.
And so, what are some of the problems that you're trying to investigate in a scramjet to find ways upon to improve?
Well, the fundamental problem with the scramjet is the how you design it smartly. It's all about efficiency. You want to make those shock waves to compress the flow, and there are two issues with it. You will never ever you can never ever afford all the space that an engine would need for you to recognize its ideal performance potential, because it takes a very, very large engine, very, very long engine, which you don't have. You are always limited by the vehicle you are going to fly this at. So then the question is, how can you make your engine as efficient as possible, given that you only have so much space to house it? That is the biggest thing. So once you have that constraint, the next constraint is how high of a Mach number can you fly? For example, the X-51 picture I showed, it had what is called a planar, a rectangular cross-section engine. And those cannot fly beyond Mach 7 or 8. Okay, Mach number is the speed divided by speed of sound. If you are at Mach 8, you are traveling 8 times the local speed of sound, right? So what we are going after is newer designs like these that I just 3D printed that are far more efficient compared to these planar, the rectangular cross-section ones. Once they're efficient, you can also get them to fly at a higher Mach number. And we can do all these things, which means that you can go with a longer range and your fuel mileage is better. So we are going, so essentially what we are looking at is coming up with very new designs, very new concepts that will help with improving the envelope of operation and the efficiency.
And so, you've also been involved in studies with developing a plasma-based flow actuators. And how do they work, and what potential problems does that fix?
So plasma is essentially you create, it's what you see around it. So your incandescent light that you have in your room is a plasma. It's a low temperature plasma. So there is a wide range of variety. Lightning is a plasma. It's hotter than the sun. So we have plasma is a very generic term to describe a whole world of things that we come to know of. So in engineering, the question is how you tame a plasma. That's the biggest thing. That's what an actuator is all about. So actuator is about how you can bring a lightning, a tame a lightning so you can make an engineering use out of it. And that's what we want to accomplish, right? And that's what we have accomplished in certain sense. So the light bulb you have is a cold plasma. We have tamed it, the plasma, to be cold. So coming to the actuator, the plasma actuator can solve multiple problems, which includes navigating, enhancing, which includes navigation and control of a vehicle by effectively altering the force distribution in a control surface around a wing around the vehicle. And it can do many more things than just that. We can control the unsteady loads that of certain, if you identify a weak component, we can use the plasma to mitigate the loads. And a plasma is also a very nice shield of electromagnetic waves. So if you think of stealth vehicles, we can one of the ways we think of with stealth is because by creating a plasma surface. So a plasma surface, if you have a plasma surface, a radar cannot see it, right? And this is used in defense and counter defense and all those things. But the fact of the matter is you have a wide array of application in plasmas. The difficulty is how you're going to tame it. It's very difficult to scale it. So if you consider like a commercial airliner, the wing is about 200 feet. It's very hard to scale the plasma actuator to such dimensions. So the effects are going to be local. But as we become smart, as we learn more about these things, we can definitely overcome these technological barrier, and that's my worldview on that.
Mhm. And what would you say has been your toughest accomplishment so far in your career?
I would probably highlight a couple. The first one is the fact that that's my PhD effort was on plasmas, and the fact that we could use and like convert a plasma source to a kinetic energy source, which was never done before. So we were able to do that, and we were able to show that we can use it at a scale that has never been done before. So, and that was pretty hard, and it was very hard to replicate as well. So, that's one of the toughest. The other thing that I would say
Oh,
Great. So, the second accomplishment that I wanted to highlight was in hypersonic platforms, and the fact that they fly very high in the sky, and to learn about um, um, how they perform, we have to learn about the flow around them. But the problem is that the flow is the pressure at the altitudes they fly is less than a thousandth of 1 atmosphere. So there's very little gas out there. And what we did was my team, we collaborated with Air Force research labs and NASA, and we developed a tool that will help us directly image and quantify uh, the loads and the flow around such vehicles at altitudes that are so high up that ours is pretty much the only tool that can actually do it. So I probably would highlight that as among the most difficult ones that I have done so far.
And is there a big milestone that you're looking forward to in your research? And if so, what is it?
So I would want to probably highlight a couple of milestones that I would personally be very excited in accomplishing. The first one is that we are building uh, so the first one is that we are building a hypersonic facility in my lab, and what we are hoping to accomplish there is to build a subscale engine, a subscale hypersonic engine with the compression systems, meaning we call that inlet. It's a compression unit, a combustor unit, and a nozzle. And the nozzle, so we can make a realistic testing of such an unit in a university scale. None of the universities or educational institutions have that facility to test a real scale engine, so realistically connected engine. So we will be one of the first to do it. Uh, that's something that I'm very, very excited about. The second milestone that I want to highlight is integrating novel materials into hypersonic and high-speed platforms. That has been one of the key challenges in the hypersonic technologies. And as I mentioned, aerospace engineering engenders and germinates new allied technologies, and one such is materials. We work with extreme materials, and one of the things I envision is integrating extreme materials in hypersonic systems and testing them out, looking at how a hypersonic flow or high-speed flow over an aero panel made of such material is going to respond. We don't know. That's a fact. So we would want to learn a lot more about how these futuristic materials are going to fare in a aero system. And so certainly we have facilities, and we work with a diverse team of researchers on those topics as well.
And final question to high schoolers like me and younger generations that want to become aerospace engineers, what would your advice be to be successful in this career?
So I would say, I personally believe that aerospace engineering is among the very few that lets you imagine completely out of the world, and no pun intended, right? You can imagine what will happen out of the world. In fact, we work on how we navigate through Mars once we have human settlements in Mars. So there's pretty much no limit on your imagination, and this is one of the very few fields that will afford you that. So we should know, it should pretty much be untethered on your imagination, because the more you can imagine the future world, the more successful you can become as a visionary. So this field has given birth to a lot of visionaries in the current and past generations, and we are sure we are going to give birth to future visionaries as well. So you should not hesitate to imagine, however crazy you think that it is, because that's how we work here. We imagine extremely out of the world things, and we make them happen. So that's one thing. And we should also understand that aerospace engineering is not a standalone unit. We benefit from many allied technologies, all the way starting from machine learning through materials. So it isn't that you are an aerospace engineer, then you are divested or disconnected from everything else. In fact, if you will be more intimately connected to many other disciplines as an aerospace engineer than if you're in any other discipline. So be prepared for a very cross multidisciplinary experience. So if you love experiencing a diversity of knowledge, this is the place to be. This is the stream to be. I think that would be my my thoughts on what who would be like, a best candidate, I guess. Once again, the academic rigor, at least in the aerospace program at the NC State, is pretty intense. So we are the training, academic training is very intensive, which is a great thing because most of our graduates work for the best of the places. So that's who we train, right? So that's another thing, right? So be prepared to dream big, and be prepared to work hard, pretty much.
All right. Well, thank you for letting me interview you, and thank you for answering questions. I think it was a great insight into your work as well as aerospace engineering in general. And have a great rest of your day.
Thank you so much, and thank you for your time, and thank you for organizing this.